Hi, welcome. So, what we're going to start today, so long we've been sort of handling boundary layers, trying to understand how a boundary layer behaves, also trying to figure out what are the effects of a boundary layer, and pretty much trying to figure out what's the purpose of this class and what are we learning here, and whether this has some application in practical life, right? So we were sort of trying to do that. Now, so far what you have seen, I don't think we've really talked about any specific equations, right, which pertain to a boundary layer. We've talked about basic fundamental equations of fluid mechanics, right. We've also done the Reynolds transport theorem, but we've really not talked about any specific equation which is for boundary layers. So what exactly will numerical equations do? So after all, these are equations, right? Well, basically, let's just put it very simply that if you solve an equation, right, numerically, using your computer, using say MATLAB, writing a Fortran code, or all sorts of computing facilities that's available today, it shall give you a knowledge of the velocity profile, and therefore that gives you a big tool in hand to understand this, and therefore you go ahead and estimate the drag, and hence use it for the application that you're looking for. So that's basically why we need equations, right? Yeah, well, they can be scary looking sometimes, but I think if we understand that where each term is coming from or what each term means, it makes sense, it begins to make sense, and then it's not so much alien. And so that's what we're going to try and do, okay? And I hope you keep up with me and don't get bored or anything, because it's very interesting as to how we will take the basic governing equations, right, which is the Navier-Stokes equation, right, and then from there we will develop the equations for a laminar boundary layer. We'll keep up with laminar boundary layer for now, okay, and see that what we are able to achieve by that, and how do we go from there to here, okay. Now, before I start, there's one more question you can ask, that you're saying basically you'll take the Navier-Stokes equation and develop boundary layer equations from there. Well, why can't we just use the boundary layers equation as it is? The Navier-Stokes equation as is. Well, to make it simpler, really. So if we do that quite a lot in fluid mechanics, where we specify problems, where we specify genre of problems, so that we can really make life easier for us. Okay, so let me start doing this, and hopefully by the end of this you should have an idea as to the final equations we get compared to the equation that we're going to start with, which is the Navier-Stokes equation. Okay, so any standard book will give you the statement of the Navier-Stokes equations, and a lot of people will write it differently. So just if you hang on with it, you'll kind of get a feel for what they mean, right? Sometimes they look a little different, but still the Navier-Stokes equation. Okay, so let me start by that, and let me say that this, what we're going to start doing now is essentially boundary layer okay. So that's what we're going to start doing now, okay. Now, what exactly are the Navier-Stokes? Okay, so this is essentially Navier-Stokes equation. I think you're familiar with this. Any standard book will basically tell you that. Now, to put it simply, okay, let me write this down first. Okay. Okay. Now, hopefully you recognize this. So this term is basically the total derivative, right? Total derivative of the velocity, which basically has the instantaneous component as well as the convective component. So we're going to, when we expand that, we will get that. Okay. Now, it's very important, and I always do this, is that every time we say Navier-Stokes equation, it's not just a bunch of letters and symbols or whatever. One really needs to understand what the equation actually means. It makes life simpler. Now, if you look at this term here, this is what? dv dt, total derivative or material derivative of the velocity, and you multiply that by the rho, right? Which is, say, you could say, just say that, think of this as a mass, multiply that by a volume, right? Now, if you do that, this is basically mass into acceleration, right? This is nothing but mass flux, right? So then this is nothing but a force, right? So what you can see here is that due to the movement of the fluid, there is a certain force which I am equating it to something here, right? So what is this something? Well, this here g is nothing but the acceleration due to gravity. Why do I write this arrow here? Well, it is just to write this in a vector notation, just simply as v. But we all know that this essentially is the I component is this, j component is 0, and it is just g in the k direction, right? So if you consider basically a normal axis coordinate system, that, right? So again, this is the gradient of pressure, right? So therefore what, and this final term, this term here is very interesting, and I would like to pull your attention to the fact that both I and j, both I and j can run from 1 to 3. What does I j mean? These are basically nothing but counters. In this case, it's just counters. So when I say, so j's, right? So say x1 basically corresponds to this x, then x2 corresponds to y, then x3 corresponds to z. It's just a way, it's notation, right? And what you see here, so similarly, when I say vi, right, it basically means u, right? I is this one, sorry, not I. So I also runs, from 1 to 3. So I and j, they both run from 1 to 3, right? So V1 is basically u, then V2 is basically v, and V3 is basically w, right? So what I'm saying is that along the x component, right, so that is, this is x1, x2 and x3, so this is u, this is conventionally, okay, this is v, and this is w, right? Makes sense? So that's what it is, and if you notice carefully, what you have here is basically del vi del xj, right, plus del vj del xi. At this point, I would suggest that revisit or just consult a very standard book as to the derivation of the Navier-Stokes equation itself, right? So it should give you an idea what this is here. This exactly means. Now what you see here is this term, I hope you recognize this, right? So this is the coefficient of viscosity. So this term, so what you see on the left hand side is basically force, right? and what you see on the right hand side are 3 terms. So this, basically what we are saying is the contribution of this force, right, on fluid comes from gravitation, right, because you got a mass. So then this is due to the gravitation. The gradient of the pressure, then we have pressure forces. So gravitation forces is basically a body force, right, it's because of that, and pressure is again with surface forces, and this, the last term here, is basically the surface forces or viscous forces, right. So, and you can see it is I and J, right. So if I were to just say J is say I is 1 and J is 1, what we will get there is del U del X plus del, right, J is also 1, del U del X, right. So we will get that. Now say keep J 1, make I is equal to 2. Then what do we get? Then what we get is del V, okay, del X plus del U, because J is still 1, del Y, right, so on and so forth. So if you continue to do this, right, so since I'm doing this, let me do this as well. So this I is equal to 2 and J is equal to 1. So let me do the other also. I is equal to 1 and J is equal to 2, right. So if I do that, then what do I get? I is equal to 1. So this is del U del Y plus del V del X, right. So that's what it basically boils down to, right. So this is, these terms that I have written is basically within this bracket, right. And for this one, if I were to calculate the total stuff, so it is basically then del xj, so which is x1, which is x, right. In this case again J is 1, so then I will get del x, right. In this case J is 2, so this is del y, right. So that's what this basically boils down to, okay, and this again is the coefficient of viscosity. So this is basically giving you an idea of the shear stresses, okay, so hence the shear forces resulting due to that. And so basically we've got gravitational forces, you've got pressure forces, and shear forces, which together form the total force acting on the fluid, right. Now from here we're going to go and find out things about the boundary layer. Interesting, right? How shall we even begin to do that? Well, let's try. Now we're going to do something very interesting. Okay, what we're going to do is non-dimensionalize. Okay, what we're going to do here, okay, so what we're going to do is non-dimensionalize. This equation, and with what? So basically what I mean is that the velocity, for example, here vi, right, say it's a u and v, right. So okay, the question is, so you can ask that why are you taking only u and v, where is w? Well, that's because I took 2D, okay. So what we're going to do here is also write this in 2D, right. We are going to write this in 2D. We're going to start with that, okay. Keep things simple, that's all. What's the reason for taking 2D? Keep things simple, that's all, right. Okay, and when I say 2D in case of a fluid, or a boundary layer, all I mean is that things are not changing in the third dimension, which I haven't considered. It's not like it's not there or anything. It's just that things are, constant and they're not changing. So so if I get a picture at one location of x and y, is the same picture which gets repeated along z. Okay. So, therefore, I do not need to do that separately. Okay, so now I am going to non-dimensionalize. So, basically when I say non-dimensionalize, so for example, u. So, u is a velocity and it has a unit, say meter per second, right. Now, I need to non-dimensionalize that, okay, so that it becomes something which does not have a dimension, simple, right. So, what we are going to do is we are going to non-dimensionalize the velocity, right, with the free stream velocity. Okay. So, okay, with the free stream velocity. Then the lengths, any length, okay, which is x, y, whatever. So, we are going to call it L, okay, we are going to call it L. Essentially, this is any characteristic length. Okay. So, when I say characteristic length, what does that mean? Well, for example, in the case of a wing or an airfoil, I said, it's the chord, right. For a cylinder, it could be the diameter, right. Depends, it really depends. So, it's the characteristic length which is what defines the flow, right. So, or which is the length of that body which is affecting the flow. Okay. So, that is the characteristic length. Okay. Pressure with rho V infinity square, okay, 2 times the dynamic pressure, and the time with L by V. What does that even mean, right? Because if you see, the unit of L is meters and this is meter per second. So, this L by V is basically, so I don't introduce another separate variable here. I just take it from here so that I can non-dimensionalize the time. So, this term here, this term that you see has units of time, seconds or minutes or whatever, right. So, now what I will do is write this equation in 2D, okay, write this equation in 2D in x and y direction. So, basically, your j shall go from 1 to 2, right, and I will go be 1, right. So, the first case, that is what we will do. So, like j will go from 1 to 2, right, and I will be 1. So, I will be 1 and j will be 2. So, what I will be using is essentially this term and this term, if you want to sort of look at that. Okay. So, if I do that, right, if I do this, let us see what we get, right. So, okay, so let us go to the next page. Okay. So, what we are saying is that we got this, okay, is equal to rho g grad of p okay, right. If I do this, so I can write this as it goes from 1 to 2 and I is 1, because that's we can write this first in the x direction, right, x direction. So, if I do that, let us expand the left hand side. What is the left hand side? It is basically del u del t plus u del x plus v del u del y plus w del u del z, right. But we said that we are going to do this in 2D. So, we are going to get rid of this term. Okay. So, we will not have that. So, we will basically have this on the left hand side. So, this part is the instantaneous and these two terms basically contribute to the convective acceleration. So, again this is equal to, now again here, so this is nothing but rho g in the x direction, which is 0. So, we will not have a component from the gravitational force, we will however have something from the pressure, and so again this is gradient. So, this gradient is nothing but del del x plus del del y. This is in 2D case. Okay. So, if I do that, so this is nothing but del p del x, right. So, yeah, well, you know, so you can, right, so it is basically an operator. Okay. So, del p del x, okay, plus, okay, so I is equal to 1 and j is equal to 1 to 2. So, if I do that, then what I will get is del x, okay, of nu del u del x, okay, plus del y mu del u del y. Right. So, if I do this, then I can write this out completely as, or, so I am going to divide by rho, right, throughout. So, what I get is del u del t plus u del x plus v del u del y, which is minus 1 by rho del p del x plus nu by rho. Okay. What do you make of this? This is del to u del x2 plus del to u del y2, right. So, if I, so that is what we get. So, this is basically the equation in the x direction, right. Now, if I non-dimensionalize this, what I will do is I will divide by v infinity. Like we said, we are going to non-dimensionalize the velocity by v infinity. So, what we will do is, now what are we going to do is non-dimensionalize. Okay. And so, to do that, what we do is we divide by v infinity throughout, right. So, if I do that, so essentially what I get is, okay, I could actually write it for you here itself. Okay. So, what okay, fine, let me not do that. So, let del t, okay, what happens now is it becomes u by v infinity, okay, then plus, okay. So, let us just, again this is u by v infinity del u del x, okay. Del x, right, plus, okay, this is del u del y v by v infinity. Is that right? Okay. So, so we get minus 1 by rho v infinity, right, or let us just say we are going to put that, we have nothing else there, right. So, then this is del p del x, okay, plus nu by rho, okay, and this is del 2 del x2 plus del 2 del y2 u by v infinity u by v infinity, right. So, we get that. So, basically when I divide by v infinity, this is what I am doing, right. Now, what we are going to do is that we are going to say that u by v infinity is equal to, we are going to just write another, denote this by another variable, right, and v by v infinity is v star, right. So, these are non-dimensional quantities v star and v. So, if I do that, right, so again, so then what happens is, so this all this term, so then okay, let me write it, okay. So, therefore, this if I were to write this, so then how does this become? So, this becomes del t of u star plus u star del u del x, okay, plus v star del u del y is equal to minus 1 by rho v infinity del p del x plus nu by rho del 2 del x2 u star plus del 2 del y2 v star. Okay. So, we need to non-dimensionalize this further, right. So, we will non-dimensionalize the time. How will we do this? We are going to divide the time by L by v infinity, right. So, if I do that, so what we are going to do is, we are going to say, so to dimensionalize that, what we will get is del, right. So, that is t by, right, L by v infinity, right. So, that you get that. So, if that is true, then I need to multiply this equation by something else, right. So, equation, or I have to multiply this entire equation by that, which is L by v infinity, if you want to look at that. So, this is L by v infinity. So, that will cancel out this thing that I am using here. So, if I do that, so basically what I am doing is, I do that L by, I multiply by L by v infinity. Okay. So, so here I use that. So, L by v infinity is something that I am going to use here throughout, right, L by v infinity. So, if I multiply L by v infinity, so I do L by v infinity u star del u del x plus L by v infinity v star del u del y, okay, is equal to minus L by rho v infinity square del p del x plus nu L rho v infinity del 2 del x2 u star plus del 2 del y2 v star. Okay. So, when I do that, okay, so what you can see here is that what I will do, without going to the next page, is that this L, I am going to use to non-dimensionalize this x, right, this, and this v infinity I am going to use to non-dimensionalize u. So, what I will basically, so I am going to just write this term here. Okay. So, what I am saying is, what we will get is this term here, u star, okay, del of u then becomes u by v infinity and x by L, right. So, then because this is u star and this is x star. Okay. So, we are also going to say x by L is x star and y by L is also y star, right. So, if I do that, then let me erase that and right. Let me also erase this and say this is u star del u star and del x star, right. Or right similarly, so if I erase that, del u star del x star, this is del y star, then yeah, so you know, we can just leave that in there, okay. And here again, well, this bit is a little more tricky because here you need, yeah, so you can use the v infinity. So you've got you know, you've got u star already there, but to get the x, you know, x star, you need L square, right. So if I need, so I basically need L square. So I can, you know, divide by L, okay. So what I will do is that I will multiply this by L square, introduce an L here, so that I still get L, and then I leave this L right here and take this L down to x here. You understand what I'm doing? So what that means is that I will erase this part, that goes, but then that comes down here, x by L this, similarly y by L this. So with what that makes it is del x star. So that's what we will write. Okay. Okay, so we will finish that. Okay, so that and that. So then what we get here is del x star 2 and del y star 2, right. So this is what you know, so nu by rho over infinity, and this part is also t star, okay. This is t star, okay. So what I will do is I will stop here and then come back into the next module and take it up right from there. So you know, work on this a little more, okay. Thank you.